Welcome you all for the course on transmission lines and waveguides. The course code is 19ECC N2301. Myself Parthiban from ECE department. So for this course you have to refresh the following subjects which you have studied in the last semester, that is your physics for electrical sciences and electric circuits and electron devices. So you have to refresh these two courses, then only you can study this transmission lines and waveguides for better. Okay, the type of the course is inbuilt. You have 5 COs. CO number 1, in this CO you will learn the different two-port network parameters like Z parameter, Y parameter, H parameter and ABCD parameters, and the difference between the lumped element model and distributed model of a line. And the second one, you are going to approximate certain parameters for high frequency analysis. So in this you are mainly dealing with the concept of standing wave ratio and the concept of input impedance and power measurement in lines. And third CO, you will select proper matching sections like half wave line, quarter wave line and 1/8 wave line for impedance matching, along with the single step matching technique for impedance match in a line. Fourth one, you have a parallel plane waveguide and rectangular waveguide. So how you are framing this structure you will study, along with the different kind of mode propagation in a waveguide you will deal in this CO number 4. Likewise, you have circular waveguides and cavity resonator. In this you will analyze the different modes of propagation like a TE mode, TM mode using the wave theory approach. So followed by you have list of experiments. Okay, so we will discuss these list of experiments one by one in later classes. Okay, so you have textbooks and reference books. Okay, in CO number 1 you have two-port network parameters, so that will be studied using this book, Circuits and Networks Analysis and Synthesis by Sudhakar Shyammohan S. Palli, and the remaining will be studied using networks, lines and fields using John D. Reddy. That is, first 3 COs will be covered in first 2 textbooks, and remaining 2 COs, that is rectangular waveguide, circular waveguide, cavity resonators, okay, and parallel plane waveguide will be studied using electromagnetic waves and radiating systems by Jordan and Baldwin. Okay, we have few reference books. Okay, so these are your reference book. Okay, so this will be your course contents. So in your course contents you will discuss these topics one by one in detail in okay. So in this session you will know the different types of guiding structures for wave propagation. Let us see one by one. So what is a guiding structure? Guiding structure is the one which carry a signal or power from one place to other. Okay, we have a lot of guiding structures. So these all guiding structures is based on the applications of electromagnetic waves. The first guiding structure is a transmission line, followed by waveguides, planar transmission lines, antennas and fiber optic guides. Okay, so out of these guiding structures we are going to discuss the first 3. The remaining will be studied in your further semesters. Okay, as I said, transmission line is one of the type of a guiding structure. So see, this is a type of a transmission line. See, the length of the line is very long. Okay, it is extended in terms of kilometer range. Okay, so this is a type of parallel wire line. Why it is a parallel wire line means we have, this is a one conductor and this is another conductor. So these two conductors are arranged in parallel. So we call it as a parallel wire line. So the length of the line is very long. Okay, it is extended in terms of kilometer range. Followed by, we have a coaxial cable. We have a center conductor followed by an outer conductor. So both the conductors are insulated in between. So this is a coaxial cable. Followed by, we have a twin lead line, and we have a twisted pair coaxial line. So this twisted pair coaxial line you normally see in telephone cables. Okay, so this will operate at very low frequencies. Okay, when you operate this twisted pair at very high frequencies, what will happen means lot of interference will come. Okay, example will be your olden day telephone cables. Okay, so it supports very low data rate. Okay, so to work on this, we are going for a coaxial line. Okay, so this will be extended in terms of meters, that is the length of the line will be in terms of meter. Perfect example will be a LAN network. Okay, so this will be your coaxial line. We can operate at a data rate which is higher than the twisted pair cable, and we have a minimum interference or minimum noise when compared to this telephone line. Coaxial cable performs far better. Okay, so this is a low frequency line. Okay, that is parallel wire line. We call another name of parallel wire line is a open wire line. So it is a low frequency, but it carries very high power. Okay, so normally you see these kind of lines in your transmission towers. Okay, so this is also lossy at very high frequencies. Why it is lossy at very high frequency means, when you operate these devices at very high frequencies, center conductor suffers from very heavy loss. So we are going for the other kind of guiding structure. So this coaxial cable operates at a frequency of in terms of megahertz range. Followed by, we have another type of transmission line, that is balanced wire line and unbalanced wire transmission line. Okay, so see this diagram. This diagram is a balanced wire transmission line. We have a transmitter and receiver. Both are connected with respect to the two lines, that is two lines are connected in parallel. So we are feeding the signal. Okay, the first line we have this signal, the second line this signal. So these two signals are 180 degree with respect to each other, and here the line is not connected with respect to ground, but the signal is which is referenced to ground. So this is your balanced transmission line. Perfect example will be your open wire transmission line. Okay, unbalanced transmission line, here the field is grounded, the voltage on the line is referenced to ground. Okay, so these are the two differences, that is unbalanced and balanced transmission line. Okay, here the voltage on the line will be 180 degree out of phase. Okay, and the signal is reference to ground. Here the field is reference to ground. So that is the basic difference between your balanced and unbalanced transmission line. Followed by the characteristics of a transmission line. So we have a coaxial cable. So we already said that this coaxial cable operating frequency range will be 100 megahertz. Okay, so these are all the different types of coaxial cable, and it says, the number says the type of the connector. Okay, so our type of the cable. Okay, so for RG8U is a type of a cable. It has a impedance of 52 ohm. We say this impedance is the characteristic impedance. We will discuss what is the characteristic impedance in further classes. Okay, and we have a velocity factor. So in terms of percentage, how fast the signal is traveling on the line, that is given by the velocity factor, followed by the capacitance in picofarad per feet is given, the size of the cable is given, and voltage and attenuation is given for different type of cables. Okay, for open line wire line, the characteristic impedance is 300 ohm. So we already said that the center conductor of the transmission line suffers from very heavy loss. Okay, when you operate the line at very high frequency. So we are going for another kind of guiding structure, that is called waveguides. It is a hollow conducting metal plate. Okay, so we have a hollow space here. So this is a type of a cable. So this is an example of a rectangular cable because the size is in terms of rectangle. So it operates at very high frequency. So this is a one type of waveguide. We call it as a rectangular waveguide. Followed by, we have different types of waveguides. This is a waveguide bend, okay, and we have a waveguide. This is also another type of waveguide bend. Likewise, we have different type of waveguides. This is a rectangular waveguide. We have a circular waveguide. So all the waveguides we are using for different kind of applications. For example, if we take a circular waveguide, that is used for a rotating section applications. So this will operate in gigahertz range. Next, you are going for a planar transmission line. Okay, so one type is microstrip line. So see this is a dielectric. So this is a microstrip, and we have a ground plane. Okay, so here also, for wave to propagate, electric and magnetic fields will be perpendicular to each other, but here some part of field lines will be going out of the air. Okay, so it doesn't support a pure TEM mode of propagation, so we call it as a quasi TEM. We will discuss what is TE, what is TEM in further lessons. Okay, you will see this microstrip line in a printed circuit board. So see this, the size of the line will be in terms of very small, that is in terms of centimeter range, but it works at a very high frequency. So we already said that we have a transmission line. We are going to deal in detail the transmission line parameters. Okay, so we already said that it is a two conductor system. So in this, we are going to discuss these concepts: low frequency analysis and high frequency analysis. Okay, so we are going to deal the difference. In low frequency analysis, the wavelength of the line will be very high. So physical size of the device is not that much important, but it carries a very high power. Example would be electrical machines and transformers. When you go with high frequency analysis, the physical size, because when the frequency is very high, wavelength will be very low. So size of the device starts playing a role. So we are going to slowly introduce the concept of space into analysis. So from this, we are going to deal in detail what is lumped element model of the line. Okay, so lumped element model means the elements can be easily separated from the network. That is called lumped element model. That is a low frequency analysis can be done with the help of lumped element model. And second one, we have a distributed model. Okay, so one advantage of the lumped element model is we can easily apply the concept of Kirchhoff's law. Okay, with the help of this, because the circuit elements, we know all the circuits. Suppose if you take a simple RLC circuit, you know what is the value of R, what is the value of L, what is the value of C. Okay, you can able to find the solution for that circuit very easily. Okay, so and the solution is simple and it is unique in nature. You will get a perfect solution. When you go for a distributed line, example will be a transmission line is a type of a distributed network. So we can't able to apply the Kirchhoff's law directly. So you have to convert the distributed network into a lumped element model and then go for the analysis. Followed by, you will study the voltage and current equations on the line and concept of reflection. Okay, and types of waveform distortion, and you are going to derive the conditions for distortionless line and the concept of loading. So with this, the session ends. We will discuss in detail in further sessions. Thank you.